Hello everyone, welcome to topic 6.4, heat capacity and calorimetry. By the end of these notes, you should be able to calculate the heat absorbed or released by a system undergoing heating and or cooling based on the amount of the substance, the heat capacity, and the changes in temperature. We are going to investigate this equation where Q equals mc delta T, what these variables mean, and how we can use them in application. This is, I believe, an equation that is listed on the equation sheet provided to you on the AP test. So the quantity of heat, Q, is the transfer of thermal energy between two bodies that are at different temperatures, from an object that is at a higher temperature to one that is colder. So energy transfers from where there is a lot of energy to where there is very little, kind of like concentration and diffusion, where you go from areas where there is a lot of the substance and it flows to areas where it is less concentrated. Heat does something similar, but we call this thermal equilibrium. Okay, there are three factors that contribute to the amount of heat that is transferred. They are the mass of the object, the specific heat of the object or substance, and the change in temperature, which is always the final temperature minus initial temperature. We don't flip those because if we keep it this way, we will always see change in temperature like a gain in energy as a positive change and a loss of energy as a negative change in the temperature. So it's always T final minus T initial. The specific heat capacity is the amount of energy needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. So each substance has its own specific heat capacity. This is if we review a little bit, an intrinsic property. It's based off of the identity of that substance, not how much you have. So water has a high specific heat capacity, whereas metals have lower specific heat capacities, usually less than 1 joule per gram degree Celsius. What this means is that it requires a lot more energy to heat a specific amount of water than it would the same mass of a metal. So metals heat up more quickly versus water that heats up much slower. The variable or label for specific heat is the capital letter C, and the units for it are joules per gram degree Celsius or Kelvin. We can use these interchangeably because the change in temperature is always going to be the same value, like quantity, if we use degrees Celsius or if we use Kelvin, because we're looking at the difference, and Celsius and Kelvin have the same numerical scale. So like 1 degree Celsius is equal to, like, 1 change per degree Celsius is 1 change per unit Kelvin. Okay. Heat is a form of energy that flows between two samples, and this is because of their differences in temperature. This is tied to our thermal equilibrium constant that we've been talking about. It is given the variable or label Q and is measured in units of joules, sometimes kilojoules, or calories. Calories is the one that you are more likely to see in like your biology class, though not always. And is also the one you'll encounter in like your daily life. Like the calorie you eat is calorie with a capital C or a kilocalorie. And so that is a way for us to like kind of make this switch between what we encounter in science and what we encounter maybe in our dietary experience. You can calculate heat when there's a temperature change using the formula Q equals mc delta T, where Q is heat, m is mass, C is specific heat capacity, and delta T is the change in temperature, which is also equal to T final minus, T initial, not equal, minus. So minus T initial. In laboratory settings, so in the lab, we would use a calorimeter to look at this. A calorimeter measures the amount of heat transferred during a reaction. A calorimeter is essentially a device that stops the transfer of heat between the inside of the calorimeter and the surroundings. So it acts as an insulator. A very easy calorimeter that we will use in class is a styrofoam cup or stacked styrofoam cups to help insulate the reaction, as you see in this picture to the left. Calorimetry is the measurement of the quantity of heat exchange. For example, if the energy from an exothermic chemical reaction is absorbed in a container of water, the change in the temperature of the water provides a measure of the amount of heat added or exchanged. The first law of thermodynamics states that in an isolated system, so one like our calorimeter, the heat cannot be lost or gained, it can only be transferred. Since a calorimeter is designed to be an isolated system, the heat lost by one substance is gained by the other. A typical experiment can be used to find the specific heat of an unknown metal by heating the metal to a known temperature and then placing the metal into a calorimeter containing water. The heat is transferred from the hot metal to the colder water until they reach thermal equilibrium. We can measure the heat gained by the water to find the heat lost by the metal. So this is actually a lab we will do in class, and we know through thermal equilibrium and the first law of thermodynamics that the heat lost by the metal is the heat gained by the water, or that they're opposite. Lost by one is gained by the other. So they should have opposite signs. And since we know that the formula to calculate the heat when there's a temperature change is Q equals mc delta T, we can substitute that in for both sides, labeling each side for metal and water as appropriate. Each substance has its own specific heat capacity, C. So comparing aluminum and lead, the specific heat of aluminum is 0.9, whereas the specific heat of lead is 0.16. Adding 1,000 joules of energy to 100 grams of each substance results in a very different change in temperature as shown below. So for aluminum, we see it has a much larger specific heat capacity, so its change in temperature is much smaller than the change in temperature for lead, which has a much smaller specific heat capacity. So you can see that when the specific heat is higher, the change in temperature is lower, and vice versa. So they are inversely related. So specific heat and delta T are inversely related. Okay. Heating a system results in the system having greater energy because the energy flowing into the system, while cooling a system results in the system having less energy as energy is leaving the system. You can see this on the heating curve for water, which is shown to the right. The specific heat capacity is a measure of the amount of energy needed to raise 1 gram of a substance by 1 degree Celsius. If we're talking about the molar heat capacity, notice the word molar is being used here. This is the specific heat capacity divided by the molar mass of that substance. It is the measure of the amount of energy needed to raise 1 mole of a substance by 1 degree Celsius. This may be provided with either one, so make sure you check which one you're using in the problem. It is usually grams, though if we're looking at phase changes, this usually is molar heat capacity, and then this one is the specific for heating a substance. Like, I don't know exactly why that's the standard in these, but you tend to be given joules per mole degree Celsius in a phase change. Not degree Celsius, joules per mole. And then in a heating curve for a specific state of matter, so solid, liquid, or gas, it tends to be joules per gram degree Celsius. Sometimes this is also kilojoules. Okay, so you just have to pay attention to what you're given and make sure you make adjustments to the amount of your substance. Chemical systems change their energy through 3 main processes: heating, cooling, phase transitions, and chemical reactions. We have seen that we can use Q equals mc delta T to calculate the heat when a temperature change occurs. In other words, when there's a change in the kinetic energy of the particles. This is shown in areas with a positive slope on the heating curve of water above. In the next lesson, you're going to look at how to calculate the heat when phase transitions take place. There's no change in temperature, so energy is being used to change the position of the particles relative to one another. So in other words, you're changing the potential energy or intermolecular force interactions. Okay, So when a phase change occurs, we need to use a different formula to calculate the heat, which I hinted at briefly above, but we will cover that specifically in 6.5. So now we're going to look at how do we apply this equation Q equals mc delta T to a practice problem. So almonds and cashews were burned in a bomb calorimeter containing water. That means bomb calorimeter means you're just setting it on fire and measuring the heat released through the complete combustion of the substance. The following data was collected. We are going to calculate the heat gained by the water for each nut. So we're going to start first with the almond because it's on the left. Okay, and so we want to know Q equals mc delta T, and it says for water. So we want to know the Q for the water. Okay, and we're using 2,000 milliliters, and the density of water is 1 gram per milliliter, so we can switch milliliters for grams when we are talking about water. So Q is equal to 2,000 grams because 1 milliliter of water has a mass of 1 gram of water. So 2,000 milliliters is 2,000 grams for water. And we're going to multiply it by its specific heat, which is 4.18 joules per gram degrees Celsius. And then its change in temperature is here. So 40 T final minus T initial. Okay, and solving for this, we end up with Q is equal to 150,500 joules. Okay, we will repeat this process for the cashew, where we have Q is equal to the mass of water, 1,000 grams times the specific heat. Oops, not 4. Joules per gram degrees Celsius times its change in temperature, which is 51.3 degrees C, minus, and whoops, I ran out of room, so 22.5 degrees C. Solving for that one, you should see that it gives off 120,400 joules. Okay. So we've calculated the heat gained, and that's why these are positive, because the temperature increase results in a positive heat gained by the water. Now we're going to calculate the energy for each nut and determine which provides more energy per gram. Well, we know that Q of water is going to be what was lost by the nut. So for the almond, that is a negative 150,500 joules. Okay. And to figure out how much per gram, we would divide this by the mass of the nut. So for the almond, it is 6 grams. So I'm going to divide by 6 grams. And performing that calculation, you should get negative 25,100 joules per gram. You would repeat this process for the cashew, noting that it is the negative of what was absorbed by water because it's being released from the cashew. So joules, and then we're going to divide that by its mass, which is 5 grams. So the 120,400 divided by 5 grams gives you negative 24,100 joules per gram. So in this, almonds provide more energy per gram. Because it is the bigger quantity that releases the most energy. Okay, so we would say that is more calorically dense because it's giving off more energy per unit mass. Okay, so now for our we do. Okay, we're going to take this in steps, and I'm going to ask you to do calculations as we go. So make sure you're ready to pause the video quickly. 50 milliliters of 0.50 molar hydrochloric acid is added to 50 milliliters of 0.5 molar sodium hydroxide. The initial temperature of the solutions was this amount, so this is our T initial. The reaction below occurred, so we have a neutralization reaction. The final temperature of the mixture is 26.3 degrees Celsius. Calculate the heat gained by the mixture. Okay, so one assumption we can make, since these are aqueous solutions, is that these two, for a total volume of 100 milliliters, these are in water. So we can say that their density is about 1 gram per milliliter. So that tells us that our total mass of solution is about 100 grams for our total solution. So we would use this as our M. And since this is in water, our C has to be 4.184 joules per gram degree Celsius. This is the value for C for water provided to you on your equation sheet. Next, you need to then determine your delta T. So we are going to set up this equation. So Q equals MC delta T. So I want you to set this up using the, and solve for Q using the mass of the solution, the specific heat of the aqueous or water-based solution, and your delta T would be based off of T initial and T final. So please pause the video and solve that now. Okay, from the calculation, you should have gotten with correct sig figs, because you are limited to 2 sig figs here, 2,700 joules or 2,700 joules. Okay, so now we're going to move on to the next one. What is the heat of reaction per mole of sodium hydroxide? So we're going to start, and I'm going to walk you through this one at for a certain spot. So we need to actually figure out how many moles of sodium hydroxide we have. Well, we know what volume and what concentration. So we can actually use conversions to figure that out. So we're starting with our volume. We know that molarity is actually moles over 1 liter. So we change first milliliters to liters. And then liters we can change to moles of sodium hydroxide. And that gives us, when you run that calculation, you should get 0.0250 moles of sodium hydroxide. Well, heat of reaction has the units of joules or, joules per mole. You could also do kilojoules per mole. Both are accepted units. So we're going to figure out the Q per mole, which our Q was from the previous problem. But since this is an exothermic process, right? This is the amount of heat gained by the mixture, right? But that's going into our water. What's released by sodium hydroxide is negative, okay? So it's being released, 2,700 joules, okay? And you're going to divide by the amount of moles you used. And performing that calculation, you should get 110,000 joules per mole, or 110 kilojoules per mole. Okay, so we're absorbing in the previous part, but it's released by us separating in this next part. Okay, it's an exothermic reaction, so the heat of reaction should be negative. So using these examples and the notes prior, complete the you do, check your answers, and thank you for tuning in.